If your agent hits a dead end and can't loop back to fix it, you haven't built an agent, you have built a script. Linear chains are one-way streets. They work in demos, but they shatter the moment real-world data gets messy. To build production-grade AI, we need to stop thinking in sequences and start architecting in states. Today we will break that chain. To build production-grade agents, we have to move beyond the sequence and into the state machine. LangGraph allows us to define cycles, turning a static line into an agentic loop. This is a paradigm shift. Instead of coding a fixed path, we are defining a set of behaviors. Our agent can now loop through a tool, evaluate the output against its goal, and decide whether to proceed or refine its logic. This isn't just a loop for the sake of it, it's the architectural foundation of self-correction. Now let's break it down. Every LangGraph is composed of two primary components, nodes and edges. Nodes are your workers, isolated Python functions that handle specific logic, like calling an LLM, querying a vector store, or executing a tool. Edges are your traffic controllers. They define the routing logic, determining exactly where the system moves next based on the output of the previous node. By decoupling the work from the routing, we gain granular control that standard chains simply can't offer. At the heart of every graph is the state. Think of this as the single source of truth for your entire agent. In LangGraph, we define this using a type dict to enforce a strict schema. Every node in your system reads from and writes to the state object. This centralized approach eliminates the chaos of passing variables manually through dozens of functions. It ensures that your context window is managed, your variables are tracked, and your data remains consistent across every cycle of the execution. Finally, we have reducers and persistence, the features that make LangGraph production ready. Reducers like the operator.add function that we will use today allow us to control exactly how new data is merged into the state. This is crucial for maintaining a clean conversation history. Beyond that, LangGraph introduces checkpointers. These allow us to save the state of a graph to a database. This enables human-in-the-loop workflows, where an agent can pause, wait for a human to approve a high-stake tool call, and resume right where it left off. Okay, now it's time to get hands-on. Let's open the terminal and create a new folder. After that, we move inside of it. We then create a new Python virtual environment, and we also activate it. After that, we install the three dependencies that we need: LangGraph, LangChain OpenAI, and Python.env. After we have installed our dependencies, we create a new file and call it .env. Here, we put our OpenAI API key. Next, we need to create one more file and call it app.py. This is where the logic will live. Now in app.py, we start with a few imports. We import operator for state reduction. From typing, we import annotated for type safety. And we also import some LangChain and LangGraph components. Here we need to notice tool node. This is a specialized utility that handles the execution of our tools. And at the end, we also load the environment variables from the .env file. Next, we need to define the agent state. This is our single source of truth. By using annotated with the operator.add on our message list, we define a reducer. This basically tells LangGraph to treat the message list as an append-only walk. Without this, nodes would overwrite each other's outputs. When we have this, we maintain a complete, immutable history of the agent's reasoning process. Now, we define the agent's capabilities. We wrap our search web function inside the tool decorator. The tool decorator is responsible for generating the JSON schema that the LLM needs in order to understand how to code the tool. We then bind those tools to GPT-4o. This binding process is crucial because it prepares the model to output structured tool call requests instead of just plain text. Next, we are defining our nodes. Nodes are the functional units of our graph. The call model node acts as the brain, invoking the LLM with the current state. The tool node acts as the hands, executing the tools requested by the model. By separating these, we can independently scale, test, and monitor the reasoning and action phases of our agent. Now, we are going to architect the flow. We will break this into three granular phases: the initialization, conditional logic, and the cyclic loop. We start by initializing our state graph. We initialize it with our schema, and we also register our two nodes. At this point, the graph is a collection of disconnected nodes. Now, we need a router to decide the agent's next move. The should_continue function inspects the model's output. If there are two calls, we route to the action node. If not, the task is complete and we route to the end. And finally, we wire the edges together. We start at the agent. We also add our conditional logic. This basically means that the application can take two routes. It can continue to action or it can move to end. Here you can see that we're also specifying an edge between action and agent. This echoes back the output of the tool to the agent for post-action reasoning. And finally here we compile our graph. And now let's define the final bit of code. We define an input dictionary with the messages key and a human message containing what is LangGraph. We also use app.stream and a for loop. By using those, we will see the state jump from the agent's thought process to the tool execution and back to the agent for the final synthesis. As you can see, this isn't a black box, it's a fully traceable state machine. Now it's time to open our terminal and run our LangGraph application. When it's done executing, we can trace what happened. First, we started at the agent node. The agent made an LLM call and decided that it needs to use the search web tool. LangGraph saw that and by using the conditional logic that we defined earlier, routed the execution to the action node. The action node executed the search web tool and returned the result. Then LangGraph again navigated to the agent node and the agent returned the final answer to the user. We have successfully mapped out the transition from static linear chains to robust cyclic state machines. You now have the architectural foundation to build agents that don't just execute tasks but reason, adapt and persist until the job is done. Remember, in production, visibility and control are more valuable than black box automation. This is precision AI engineering. If you enjoyed the video, please subscribe to the channel to level up your implementation stack.